Good morning. In the last lecture, we were looking at the response of a single degree of freedom structure to harmonic loading. Okay? We will continue looking at the response to harmonic loading today because there are several things that I wish to continue, talk more about on this. In the last lecture, I stopped with something called the Argand diagram, which is essentially a representation of all the forces and a displacement, velocity, acceleration responses in a complex plane, because that gives you an idea of how the equilibrium at any instant of time t is maintained in the structure. Okay, so, but before I continue with the Argand diagram, I would like to do a quick review of what we had looked at last time. If you remember, the equation that we solved this was the equation that we had solved, and what we said was, well, this has two parts, a homogeneous part and a particular solution, and we saw that the homogeneous part was really a free vibration equation solution, and the particular part was what we called as the steady state solution, and the steady state solution was what we were interested in, because we said that by and large the transient dies out over a period of time, as long as the structure has some amount of damping in it, any amount of damping. Okay? It is just that the transient part takes longer to die out if the damping is small, and it dies down quicker if your damping is large. Okay? That is the only thing. So, therefore, we saw that the solution came out to be of this form, and that is the steady state solution. The steady state solution came out to be where u0 is equal to P naught upon k, and theta is equal to, I am sorry, there is a d here. So, theta is tan inverse of 2 xi beta upon 1 minus beta squared, and d was equal to 1 upon 1 minus beta squared the whole squared plus 2 zeta beta the whole squared, and the entire thing under square root. And if we look at this d and theta, they took up the form as we will look at in the next slide. If we look at it, this is the dynamic amplification factor d, okay? And if you look at it, these are for different values of damping. This is for 1% damping, 2% damping, 5% damping, 10% damping, 20% and 70%. And if you look at it, okay, if you look at 1% damping, it is exceedingly high. For 2% damping, the dynamic amplification factor, peak dynamic amplification factor is 25, and if you look at 5%, then you have 10, and this again is very obvious. If we look at d, d is equal to 1 upon square root of 1 minus beta squared plus 2 xi beta the whole squared square root. So, if I put beta equal to 1, which is what we call as resonance, where the excitation frequency is equal to the natural frequency of the structure. Okay, if we substitute that, then D turns out to be equal to 1 upon 2 xi. Okay. And so, if xi is equal to 1%, D max, by the way, this is D resonance. So, it is not D max, it is D resonance is equal to, let us look at it, 2 into 0.01. So, that is 50 for xi equal to 5%, D resonance is equal to 0.05. So, 10. So, if we look back at this at the slide, you will see that at resonance this is equal to 10. Similarly, if you look at 20, it is equal to 5, sorry 10%, it is 5, okay, and 25. So, this is how your dynamic amplification factor looks, and if we look at the next slide, this is nothing but this tan inverse 2 zeta beta upon minus this thing. And if we look at, remember last time I had talked about it, and we had said that this theta, if you looked at theta at beta equal to 1, this becomes tan inverse of 2 xi upon 0. So, that is tan inverse of infinity, which is pi over 2 or 90 degrees. Okay. So, the thing that we saw was that irrespective of what is the damping at the resonance, the phase angle is pi by 2 or 90 degrees. And we also saw that if for theta beta less than 1, this is tan inverse of 2 zeta beta minus 1 minus beta squared. This term is positive for beta less than 1, and therefore, if this is positive, then theta is between 0 and pi by 2, or in degrees 0 and 90 degrees. And this is what you see in this, that if beta is less than 1, the phase angle is less than 90 degrees, between 0 and 90 degrees. At beta equal to 0, of course, it is 0 by 1. So, theta is 0 irrespective of any this thing. And please also note that since this is tan inverse of 2 xi beta upon 1 minus beta squared, if xi is small, okay, irrespective of beta, if xi is small, this value will remain small for a larger value of beta till it suddenly jumps up to 90. If the xi is larger, then it starts growing larger. So, you see, for a particular value of beta, if you look at it, at 0.8, if xi is equal to 1%, it is almost 0. Xi equal to 2%, almost 0. Xi equal to 5%, well, it is about 10 degrees. Xi equal to 10%, it is about 20 degrees, 25 degrees, and so on and so forth. So, the point here is that the phase angle when beta is less is between 0 and 90. When theta is greater than 1, then tan inverse 2 xi beta 1 minus beta squared. Note that this term becomes negative. If this term becomes negative, then theta basically goes between pi by 2 into the second quadrant, pi by 2 to pi, or between 90 degrees and 180 degrees. So, that is what happens, that if beta becomes greater than 1, okay, then this aspect essentially becomes that it goes beyond 90 degrees, and if you take 1.2 for instance, you will see that all of them are between 90 and 180 degrees, or between pi by 2 and pi. And the point again to note is that if you have a very low damping, note what happens. It's 0 till it comes close to 1. At 1 it's 90 degrees or pi by 2, and right after it goes beyond, it becomes practically again 180 degrees. So, it flips, okay, and that is understandable, because when it flips, okay, this is going to almost 0, and if it goes to 0 from the negative side, limit of tan inverse 0 going from the negative side is pi by definition. So, that is what you have. Okay. So, this phase response is a very important aspect, because irrespective of damping, okay, this phase between the steady state and the loading, the phase between this and this becomes 90. So, if we use this 2 channel, 2 jacks, one input with the loading and one input with the response, which is a steady state response, okay, you will see that essentially these being 90 degrees out of phase implies that they become a circle. So, if you look at, it's very easy to see when resonance occurs, and in fact you can find out the natural frequency in that manner for low damping values, is by looking at this xy plot, and the xy plot remains like this when it is they are in phase, okay. And so, assume a very low damping 2% damping structure, it remains like this till it hits resonance, then it becomes like this, okay. And as soon as it crosses resonance, it goes back to something like this. So, you see the resonance can be picked up very, very easily, and we saw that resonance is where the excitation frequency is equal to the natural frequency of the structure. So, this is actually a beautiful way of finding out the natural frequency of a structure. Okay? So, now the other question that becomes is, since we saw that at D at resonance is equal to 1 upon 2 xi, actually you can do xi is equal to 1 upon 2 d at resonance. And what is d? D, if you look at it, is nothing but 1 upon 2 the US max upon U0. So, this basically becomes U0 upon 2 US max. So, in other words, going back to the previous one, if I find out, if I look at the displacement response and I find out this value is nothing but this value here, okay, and I keep looking at the dynamic amplification factor and I go like this and I see what the maximum value is, read off the maximum value. So, here for example, on this structure I read off the maximum value, I see the maximum value is 10 times ux. So, this becomes, so this is 1 upon 2 into 10. So, this is 1 upon 20. So, xi is equal to 5%. I know that the xi is 5%. So, in a way, this is another way of finding out the omega, because this, when you get resonance, you get this to come like this. So, you know that the phase angle is 90 degrees. That tells you what value of omega at which this is. So, this one gives you the omega, the natural frequency of the structure, and this gives you the damping. So, in other words, this is another way of finding out the dynamic characteristics of a structure. Now, what I will do before I continue, I will remember last time I said that what if you have a structure which has the following, is subjected to this kind of loading. It is a harmonic loading, but it is subjected to P naught cosine omega bar t. Remember I had said, and I had said that you should do it through yourself. Now, what I will do is, let me just solve this problem for you. Okay? You must have already tried solving it, but I'll go through the steps. Okay? Very, very easy steps. I am only going to do the steady state solution. So, steady state solution, what form does it take up? Remember that it always takes up the form G1 plus G2 cosine omega bar t. So, this is the form that it takes up, and if I the calculate U s of d is equal to omega bar G1 cosine omega bar t minus omega bar G2 sine omega bar t, and U double dot s of t is equal to omega squared G1 sine omega bar t minus omega bar squared G2 cosine omega bar t. So, if I substitute all of these into this above equation, what I get is the following, and then I just collate the sines and cosine, and then I get minus m omega bar squared plus k G1 minus c omega bar 2 G2 sine omega bar t plus omega bar c G1 plus m omega squared plus k G2 cosine omega t. Okay. So, this is the left hand side of the equation, and this is equal to P naught cosine omega bar t. So, if that is the solution, then what happens? We get the following. We get that omega bar c G1 plus k minus omega squared m G2 is equal to P naught, and we get k minus omega squared m G1 minus omega bar c G2 is equal to 0. Now, remember I had said last time that divide both of the equations by k, and what did we get? I am not going to go into the details, we have already done it last time, please review it. this will imply that I get that 2 xi beta g1 plus 1 minus beta squared g2 is equal to p naught, and 1 minus beta g1 minus 2 xi beta g2 is equal to 0. So, if these are the two equations and I solve them simultaneously, oh, by the way, this is p naught upon k, because I have divided both by k, 0 by k is 0. Okay. So, if this is the equation, these are the two equations that I solve for, and if I solve for them, I get that G1 is equal to P naught upon K 2 xi beta upon 1 minus beta squared plus 2 xi beta squared, that is G1, and G2 is equal to P naught upon K into 1 minus beta squared upon 1 minus beta squared plus 2 xi beta the whole squared. Okay. So, that is G1 and G2, and therefore, the solution then becomes the following. Solution becomes US of t is equal to, I am going to put P naught by K and 1 minus beta squared plus 2 xi beta the whole squared outside, and what I get inside is 1 minus beta squared cosine of omega t plus 2 zeta beta sine omega t. This is the solution. This is a steady state solution of when you subject it to P of t equal to P naught cosine omega bar t. Now, note something very interesting, and that is that once we do that, okay, what happens? If you look at this particular solution, remember, what is cosine x minus y? Cosine x minus y is cosine x cosine y plus sine x sine y. Okay? That, remember that. Once you remember that, then you will see that this solution becomes obvious. This solution becomes the following. US of t is equal to P naught by K upon 1 minus beta squared plus 2 zeta beta the whole squared. Okay, and let's look back at this, right? This is cosine x cosine y plus sine x sine y. So, this is sine x, this is cosine x, okay? And if I look at the two of them together, okay, it becomes what? It becomes 1 plus beta squared plus 2 zeta beta the whole squared half. So, this one gets cancelled. So, this becomes again half, and what we get is cosine omega bar t minus theta, where by definition theta is equal to sin x upon cosine x. So, that is tan x, and so that is tan inverse of 2 xi beta upon 1 minus beta squared. Look at this solution, excepting for the fact that this is p of t p naught cosine omega bar t, and therefore, you have cosine here, but if this was sine, you would have sine here with exactly the same theta and exactly the same dynamic amplification factor, because US upon US max upon P naught upon K is equal to 1 upon this, which is again D, the same as what we have shown here. So, note that this dynamic amplification factor and this phase response are both equally true, irrespective of whether your it's a sine omega bar t or a cosine omega bar t or a linear combination of the two. So, therefore, for any harmonic response, this is the dynamic amplification factor and this is the phase response. So, although I had originally developed it last week for sine omega bar t, this week I have shown it to you that this is equally valid for cosine omega bar t. Okay? So, once we have this, now let me go back to the Argand diagram that I was looking at. So, I would like to again go back to the Argand diagram, and in the Argand diagram, let me again restate the solution process. If you look at it, I will just do this for now sine omega bar t, or I mean it does not matter, I will do it for sine omega bar t. So, US of t is equal to, I am going to say u0, where u0 is into d into sine omega bar t minus theta. So, note that now this solution that I have, although I have sine here, this is equally valid for any arbitrary. Only thing that is going to happen is that the response, displacement response is going to lag the forcing response, which is the load response, by theta. That is a given, and that theta, we know what that theta is. That is this phase response that I have shown over here. Okay? So, now the question then becomes, so theta is a known value. So, let me just go back, that you have, this becomes what? Let's plot it. This becomes u naught d omega bar cosine omega bar t minus theta, and u double dot s of t becomes minus u naught d omega bar squared sine omega t minus theta. Now, these are the displacement, velocity and acceleration. And let me look at p naught of t. P naught of t is sine omega bar t, right? Okay. So, let us be very, very clear about this. Okay. So, if I were to plot it on the Argand diagram, how will it look? Now, I am coming back to the Argand diagram. Okay. How does it look? Well, let us plot it. This is the real axis, this is the imaginary axis, and what did we say was the Argand diagram? Well, the Argand diagram is such that this value, which is a real value, is really the, if I plot a vector, okay, so if I plot p naught sine omega bar t, so I am going to plot vector of magnitude, again what is the magnitude? P naught. So, I am going to plot a vector p naught, and what we say is that look, the projection on this axis, So, in other words, on the real axis. So, projection on the real axis of this vector should be this. Okay. So, how was that then? Well, let us look at it. If I were to call this as omega bar t, okay, look at it. This represents the real plane, and that is P naught omega sine omega bar t. Understand? Because this is 90 degrees. Okay, this is a vector. So, in other words, remember again that the Argand diagram is nothing but a representation of the each response quantity in a complex plane, such that the real part on the real axis, okay, the real projection of the vector always represents the vector, the real vector that you have. So, similarly, let me put it this way. So, if this is P naught sine omega bar t, this is a vector that lags that by theta. So, what does that mean? That is a vector that lags. And what is that vector? u0d. So, this vector is u0d, and it lags by theta. Note that if I plot this, this becomes omega bar t minus theta. So, then if I look at the real projection, you get u0d sine omega bar t minus theta, which is what this is. Okay. So, this vector represents the displacement vector. Okay. Now, let us look at what this is. Look at this vector. It is cosine omega bar t minus theta. So, if I were to look at this and look at, remember, cosine always leads the sine by 90 degrees. So, if I were to look at cosine plot, this would be in this fashion. It would be 90 degrees to this line, okay, where what is this one? This one is omega bar t minus theta, and this value is u0 d omega bar. So, what does this? So, this vector represents the load, this represents the displacement, this now represents the, and look at it. If you look at this, the projection on the real axis of this is what? u naught d omega bar into cosine of omega bar t minus theta, which is what we have here. Okay. So, this represents, this vector represents u dot, this represents u, this represents p, and finally, if you look at this one, all this is, the acceleration is minus of sine omega bar t. So, minus means just the opposite direction. And what is the value? The value is equal to u0 d omega bar squared. So, this represents u double dot. And if I look at it, if I take the plot, okay, where what is this one? This one is omega bar t minus theta. And if you look at this, if I look at the projection of this, it becomes what? This one becomes u naught d omega bar squared into sine of omega bar t minus theta, but since it is on the negative real axis, it is negative and it represents this. Okay. So, the first Argand diagram that I have drawn represents what? Represents the displacement, the velocity, and the acceleration. Okay. Now, next Argand diagram I am going to draw is going to be purely on the forces, force equilibrium. So, if I look at it, what does it become then? Okay, let's look at this particular aspect. Okay. If you look at this, US is equal to this. What is the elastic force? I will call it Fs of t. Fs of t, if you look at it, the if displacement is in this direction, okay, the force opposes it. So, it will always be minus k into us of t. Okay. Let us look at the damping force. Damping force, if you remember, I have talked about it. A damping force is a damper, a viscous damper, where if a velocity is in one direction, the damper opposes that velocity. So, that is c into us dot. And finally, the fictitious inertia force that we talk about, which is if any body has mass, okay, it resists it. You know, if a body is accelerating in a particular direction, what does Newton's second law says? Well, there is a equal and opposite, you know, kind of an inertia force that is proportional to the velocity to the acceleration, but opposes it, and that I call as inertia force, and that is equal to mu double dot t. So, we put this and then I plug in the values and the directions. What do I get? This is equal to minus k u naught d sine omega bar t minus theta. This is equal to minus c u 0 d d omega cosine omega bar t minus theta, and this is equal to minus m u naught d. Note, it is not minus because this is also this itself is minus. So, minus minus becomes plus m u dot d into omega bar squared sine omega bar t minus theta. So, these are the forces. Note that this plus this plus this is equal to P. Okay. So, now let me just go through a few steps here. Okay, I am going to plug in the value of u naught in here. U naught is equal to P naught upon k. So, this becomes then our F s of t becomes equal to minus P naught d into sine omega bar t minus theta. Okay. Now, again I am going to plug in P naught upon k here, and remember c omega bar upon k is equal to what? 2 xi beta. We have already derived this, so I am not going to derive it again. So, basically f d becomes equal to minus P naught into 2 xi beta d cosine of omega bar t minus theta, and f I of t. Well, let us look at this. This is P naught upon k. So, this becomes m omega bar squared upon k, which is beta squared. We have already seen that. So, this is equal to P naught into beta squared d sine omega bar t minus theta. So, having written these, let us look back at these. You note that if you look at us of t and the F s opposes that. Okay. So, if u of t is in this direction, your F s is in the opposite direction. Similarly, if you look at u dot s, if u dot s is in a particular direction, cosine, this is minus of cosine. So, if u s is in this direction, f d is in this direction. Okay. And finally, if you look at it, I am going to show this. If you look at, let me just show this. If you look at f I, it's sin omega bar t, it's in this particular direction, where this is in the opposite direction. So, if you look at this, this is in the direction of US and Fs is along the direction of US. Okay. So, if I plot the Argand diagram now, what does it become? Now, I am going to draw the force Argand diagram. First, I drew the force Argand diagram, and let us plot it again. Real, imaginary, and remember P naught is in this direction with omega bar t. Then this was the direction of u. So, therefore, just the opposite direction would be Fs. And what are the units? What are the dimension? Magnitude. Magnitude is P naught d. So, it is going to be, this is going to be omega bar t minus theta, and this, the magnitude is going to be P naught d. Okay. Now, remember, this was the direction of the velocity. So, this will oppose it. Your damping force is going to be equal to P naught into 2 xi beta d, where this is omega bar t minus theta. And finally, remember Fi is sin omega bar t, P naught B naught. So, therefore, this one will be in this direction, and it will be P naught beta squared d, where this is omega t minus theta. Now, note I have made an assumption here. What is the assumption? That theta is between 0 and pi by 2. In other words, a priori I have made the assumption in this Argand diagram that beta is less than, I am sorry, theta is less than pi by 2, which basically means that beta is between 0 and 1. Now, let us look at this particular one. How does it look? Now, if you look at this, what we are saying is that this triumvirate, where this is 90 degrees, this is 90 degrees, these triumvirate of forces, which this is Fs, this is Fi, sorry, Fd, and this is Fi, Fs plus Fd plus Fi is equal to P of t. So, this is Fs of t. So, in other words, if I take a snapshot at a particular instant of time t, this is a snapshot. These three together equilibrate this. Okay. So, this plus this. So, vector addition of this plus this plus this is going to be equal to the, is going to give me a vector which is along this line. Okay. Now, then the question becomes, okay, how do we tackle this problem? How do these three, and note that this, as t varies, this t would imply that this will go like this, but these three are connected to P and will also move with it. So, in other words, this interplay, that this is going to be phase lag. Now, the inertia force phase lags the applied force by theta. The elastic force opposes that inertia force, and this opposes is at 90 degrees, because it is proportional to the velocity and opposes the velocity. And remember that velocity is 90 degrees out of phase with acceleration and displacement. Okay, we have seen that. Now, this is a very interesting thing. Now, I will show, it is very hard for me to show that these three meet together, but if I were to look at it in the real plane, okay, let us try to see what this represents in the real plane. This representation on the real plane is going to be equal to, let us look at this. This is the representation of the real plane. So, the representation of the real plane, if I plot the Fi representation of the real plane, what is that going to be? That is going to be equal to P naught d sine omega bar t minus theta, and this is minus because it is along the negative. So, this is the, this represents the real part of the spring force, okay, negative. Right. Now, let us look at this one. This is it, and so that is going to be equal to P naught beta squared d into sine, note that this is plus, okay. So, I have put this plus this plus this. So, this one is going to be equal to plus P naught. So, it is going to be P naught into 2 xi beta into d cosine omega bar t minus theta, and note that this is on the negative plane. So, this will actually be, this should be negative. Okay. This is equal to P naught, right, because we have said that all of these are together. Now, let us see if this makes sense. Does this make sense? Sin omega bar t goes together. So, then this becomes, then what does this become? This will become 1 minus beta squared P naught d sin omega bar t minus theta minus P naught 2 xi beta cosine omega bar t is equal to P naught sin omega bar t is equal to P naught sin omega bar t. Okay. Now, let us look at this. How do we, this is cosine omega bar t minus theta. Now, how do we show that this is equal to this? Well, let us go one step further. So, this Argand diagram I am proving to you in a roundabout manner, and that is that, let us see how do I get these two together. If I look at these two together, okay, I am going to plug in the value of theta in here. So, if you look at this, I am going to expand these. If I expand these, what do I get? I get 1 minus beta squared into d into P naught is equal to, well, on this side I get sine omega bar t cosine theta minus cosine omega bar t sine theta. Okay. And on this side I will get P naught 2 xi d into cosine omega t cosine theta plus sine omega bar t sine theta, and this is equal to P naught sine omega bar t. Now, let's just go through with this. If you look at it, let's just look at what we get here. What are d? D, if you look at it, is equal to 1 upon 1 minus beta squared plus 2 xi beta half, and theta is equal to tan inverse 2 xi beta upon 1 minus beta squared. Okay. So, look at it, tan theta is equal to 2 xi beta upon 1 minus beta squared. Okay. That is tan theta. Okay. So, so that means if we look at this, then what becomes sin theta? If tan theta is this, look at it, let us look at the thing. This is theta. Okay. Tan theta is what? This upon this. So, that means we are saying that this is 2 xi beta, this is 1 minus beta squared, and so what is sin theta? Sin theta is this upon this. So, sin theta is 2 xi beta upon square root of 1 minus beta squared plus 2 xi beta square root. Pythagoras theorem, this squared plus this squared, square root of that is this. Okay. And so, what is cosine of theta? Cosine of theta, if you look at this, is this upon this. So, that is 1 minus beta squared upon, if you look at this, what is this? This is nothing but d, right. So, I am going to put this as d. So, having put these in, let me plug these into these equations that I have here. So, this is nothing but, let us look at this. So, this becomes what? Cosine is 1 minus beta squared upon d, and sine is 2 xi beta upon d. So, d cancels out, and so what am I left with? I am left with the following. I am left with this 1 minus beta squared. The d goes out because d is come out. So, sin omega bar t into, what is this one? Cosine. Cosine was 1 minus beta squared upon d. So, d is gone out, and the other one is cosine omega bar squared into 2 xi beta upon d, again that is gone. So, this is what it is, minus p naught into 2 xi beta. The d goes inside. So, if the d goes inside, this becomes cosine omega bar t, and what is cosine theta? 1 minus beta squared, right. The d cancels out, and the other one is sin omega t into sine. So, that is 2 xi beta, the d cancels out. So, this is what I get, okay, and is equal to p naught sin omega bar t. Now, let us look at this, let us put the sines and cosines together. What do I get? I get the following. I get, okay, I am just going to rewrite this, I am going to put it all together, and so this into this is going to give me p naught 1 upon beta the whole squared. So, I am going to put that in. I am going to get p naught 1 minus beta squared the whole squared sin omega bar t. Then I am going to take this one sin omega bar t, which is nothing but minus p naught, right. It is in minus p naught. Okay. So, this one becomes 2 zeta beta squared. So, this becomes then minus p naught, okay, into 2 zeta beta squared sin omega bar t, and then I will put together the other terms from here. Okay. I am going to incorporate these terms from here, and so what I get is cosine becomes then minus 2 xi beta into 1 minus beta squared and minus p naught into 1 minus beta. You see the cosine term disappears. So, cosine term disappears, and what I am left with is that 1 minus sine squared, that is what I am left with. Okay. So, if you look at this, okay, ultimately this term then becomes equal at all times to P naught. Okay. So, I have shown in a broader sense, by taking the real one, I am able to show to you that P naught is equal to P naught. That is what you get. Okay. So, they are indeed in equilibrium. Now, I am going to stop here today, and next time I am going to take up and show to you that for specific situations of when beta takes up specific values, what happens to the Argand diagram. Thank you. Bye.